You pop a pill for a headache, an infection, whatever it is, and you trust that inside that little tablet, there's a powerful molecule ready to get to work. But what if, for a lot of the most promising new drugs, that's just not the full story? What if the biggest challenge isn't even discovering the drug, but just getting it to work in the first place? I mean, it's a thought we've all had, right? You take something and you think, is this thing doing anything? It seems like a simple question, but it actually opens up a massive challenge in the world of medicine, because for a surprisingly huge number of drugs, just getting them to work inside your body is the hardest part of the entire deal. That's right. According to scientific estimates, a staggering 40% of newly discovered drugs have a fundamental problem. A problem so basic, it can stop them from having any effect at all, no matter how powerful they are in a lab. So what is this roadblock? Well, it all comes down to one crucial word: bioavailability. The concept is pretty simple, really. For a drug to do its job, it has to get into your bloodstream. If you swallow a pill and it just passes right through you without being absorbed, it's totally useless. It honestly doesn't matter how brilliant the drug is. If its bioavailability is zero, its effectiveness is also zero. Okay, so let's dig into that. What exactly is this pill problem that affects so many potential new medicines? The root cause is, well, surprisingly simple. This is step one, and it's completely non-negotiable. Before a drug molecule can pass through the walls of your gut and into your system, it has to dissolve in the fluids that are in there. If it can't dissolve, it can't be absorbed. It's really that simple. And here's the issue. A lot of modern drug molecules are hydrophobic, which literally means water-fearing. They behave just like oil and water. They refuse to mix, so they just stay as these tiny solid particles and, well, they get flushed right out of your system. What we really need is for them to be like sugar and water, dissolving easily so the body can actually put them to use. So you've got these amazing, potentially life-saving oily drugs that our bodies just can't absorb. How do you fix that? Well, scientists have come up with this incredibly clever workaround called a solid dispersion. The official definition sounds a little technical, I know, but the idea behind it is absolutely brilliant. You take your hydrophobic, water-hating drug, and you mix it at a molecular level with a hydrophilic, water-loving substance. We usually call that second part a carrier or a matrix. Let's just go right back to our analogy. The sugary carrier dissolves in water almost instantly, and because the oily drug molecules are spread out and basically trapped inside it, they get pulled along for the ride. They're forced to disperse in the water, essentially tricking them into dissolving when they absolutely wouldn't on their own. But this isn't just some simple party trick. There are actually several really powerful scientific principles at play that make these solid dispersions so incredibly effective. So the key takeaway here is that this is like a multi-pronged attack on the problem. By dispersing the drug molecule by molecule inside the carrier, you've basically shrunk its particle size down to the absolute minimum. This massive increase in surface area, plus the improved wettability from the water-loving carrier, means water can just attack and dissolve it from all sides. But that last point on the list, that one is arguably the most important of all. To really get why, think about how most solids exist in a crystalline state. It's like soldiers locked in a perfect rigid formation. It takes a ton of energy to break that formation apart. But a solid dispersion traps the drug in a high-energy amorphous state, which is more like a disorganized, chaotic crowd. The molecules are all jumbled up, they're not locked in place, and that makes it much, much easier for water to just pull them apart and dissolve them. Now, creating this perfectly mixed up, jumbled state is a really precise science. So how do chemists and pharmaceutical scientists actually pull it off? When you get right down to it, it really boils down to two main strategies for getting that drug and carrier to mix at the molecular level. You either heat them up until they melt into one single liquid, or you find a common solvent that can dissolve both of them at the exact same time. Okay, so with the solvent method, you take your oily drug and your sugary carrier, and you dissolve them both in some kind of liquid solvent. Now they're perfectly mixed. The real trick is then to get rid of that solvent so fast, often by spray drying it in a hot chamber, that the drug and carrier molecules are kind of flash frozen in place, locked together in that high-energy amorphous state we were just talking about. The other main approach, the fusion or melt method, sounds even simpler, right? You just heat the carrier till it melts, then you stir the drug in until it dissolves, kind of like making candy. But, and this is a big but, it has a major drawback. A lot of drug molecules are really delicate. The high heat you need to melt the carrier can actually destroy the drug before you even get a chance to make the pill. So if this technology is so fantastic, why aren't all poorly soluble drugs made this way? Well, like with any advanced tech, there are some pretty significant real-world hurdles you have to get over. Probably the biggest challenge is stability. Remember that high-energy, disorganized crowd state? It's fundamentally unstable. Over time, those drug molecules really want to snap back into their comfortable, low-energy soldiers in formation crystalline state, which of course would make the pill useless again. Add that to the challenges of scaling up these complex processes from a lab to a giant factory, and you can see why it's not always the easy answer. But here's the really exciting part. Scientists haven't just given up. Instead, they are constantly inventing these new and clever ways to make solid dispersions more stable, more efficient, and way easier to manufacture. And these solutions are just so clever. For example, instead of some complex multi-step process, scientists can just spray the mixture directly onto tiny sugar spheres. To avoid heat damage, they figured out how to use low-temperature melts that can be poured right into capsules. And then you have these futuristic techniques like electrospinning, which creates nano-sized fibers, maximizing that surface area for dissolution even more. And this stuff isn't just a theory in a lab. It's already being used in drugs you can get right now, like Spornex. They use that sugar bead coating method. A super thin film of the drug and its carrier coats the bead. When you take the pill, that film dissolves and releases the drug at a concentration that's way higher than it could ever reach on its own. That's what allows the body to finally absorb it. Which brings us to the final and I think most crucial question. Just think about it for a second. That 40% of new drugs that often get abandoned early on because of this solubility problem, what's in there? What potential cures for cancer or Alzheimer's or new viral diseases are just sitting on a shelf somewhere, not because they don't work, but simply because we haven't figured out the right trick to get them into our bodies yet? Solving the pill problem isn't just a fun chemistry puzzle, it could literally unlock a whole new generation of medicine.